Let's do a little overview of our most recent integration assignment. So I'm going to go through the 4 solutions where I discuss them and explain out my solutions. I do suggest some of you go back and look at your work um, to redo some of these questions, even if you had correct solutions. Some of you are passing in work that is not your work. You don't understand what's on the page. If I was to ask you to give me an explanation of what's written down on your page, you would not be able to. I'll give you an example of that. So I just picked out 4 samples of work from, I think it's question, that's the last one, letter D. So letter D ended up doing a by parts. If you look at these 4 samples of student work, I can clearly tell that these 4 students collaborated. Collaboration would be fine if you said, oh yeah, you got to use by parts, and they say, oh, okay, I see what you mean now, and then the student went and did it on their own. But looking at these 4 examples, clearly that is not as what happened. I can tell that these 4 students simply took a picture of their work, shared it amongst each other, without actually getting a clear understanding of what was going on. They just chose to copy that student work. You say, well, how do you know? How can you tell that? Here's how I tell. And again, this is to help you in the future. This is a very serious offense at a post-secondary school to plagiarize your work, which means get someone else's work and just copy it verbatim. Again, as I said, I have no issue with you asking questions amongst your peers, asking questions to me, searching YouTube, searching Google. Those are resources that you have. But taking someone's work and copying it verbatim is a serious offense. If you look at these 4 words, the piece of work, watch this. That sign right there is the dead giveaway of plagiarism, because it's an equal sign that's out of place. It really shouldn't be there. It's in this person's work. It's in this person's work. It's in this person's work, and it's in this student's work. One student, yes, could put an equal sign erroneously in the wrong place. 4 people putting the same wrong equal sign in the wrong place is a clear indication of plagiarism. So please, in the future, do your own work. I would much sooner you get to a point and say, I got stuck here. I tried. This is what I got. And again, you have to try. You have to put some things down on the page. You have to go back and watch questions in the videos that are similar to ones that you're doing. And they're not all going to be exact. That's part of the challenge of taking these kinds of courses. So you notice that the questions I'm giving you, I'm citing where I'm taking them from. It is what you're going to be expected to do at a university level next year. And if you say, well, I can't do that work, I'm not sure how to tell you. This is what you're going to be into next year. So it's time to figure out, how am I going to manage this stuff? Because it is what you're going to be paying a lot of money next year to try and manage this type of work. So that falls on you. So please don't pass in stuff that is somebody else's work that you don't understand. Another giveaway here is that when I did integration by parts and showed you how to do it, I always set it up with the U here and the DV here and work this way. And I'm not saying you have to do it that way, but generally what students do is they model what they are shown. I never showed how to do it by parts this way, and here's 4 students doing by parts going sideways rather than down the way that I had shown them to do it. Again, an indication that the work was shared and probably not something that they actually understood what was going on. Because if someone had said, oh, well, you got to use integration by parts, I'd say, oh, yeah, I remember how that works. And they would have probably looked at the video and did this. Okay, so there's my rant for today. So let's get on to the actual solutions and show you how I would have done. I'm not saying that these are the only solutions, but these are how I would have done these questions. Okay, so when I saw this one, I see this square root sign here. I wish this had been a 4 or a 9 or a 25, would work better, but it doesn't have to be a perfect square. I would set up a triangle to model this square root. So I would put radical 2 here. I would put x on this side, so that then when I did Pythagoras' theorem to get my third side, it would be the hypotenuse squared, which would be 2, minus the other side squared, which would be x squared, and then you take the square root of it, and that would make this side the square root of 2 minus x squared. Now, I need to rebuild this integral. So what I do is I need something for the square root of 2 minus x squared. So I go here. There's the square root of 2 minus x squared. So I want a trig ratio that involves that side and a number. I don't want the x to be brought into it. So it's going to be cosine of theta would be the square root of 2 minus x squared over radical 2, which means radical 2 multiplied by the cosine of theta could be put in there instead of the square root of 2 minus x squared. That's why they call it trig substitution. You're trying to find trig ratios to put in there instead of the algebraic version. All right, that takes care of the numerator. I need something to put in there for x. Well, x is one of the sides of my triangle, so I'm going to use these two sides. Again, I want x and a number, so I'm going to go sine of theta is the opposite over the hypotenuse, radical 2 multiplied by the sine of theta. That could be put in there instead of x. That'll take care of this. So then the only other substitution we need is something for dx. Dx is found by taking the derivative of x. Root 2, the derivative of sine is cosine theta. D theta, the derivative of x is normally a 1, but remember this is d theta over dx, and we multiply both sides by dx. I showed you that little shortcut. All right, so here's all the information we're going to use. Now I'm going to reconstruct this integral using trig substitution. The numerator, we are going to put in there root 2 cosine theta in this place. The denominator, which is x. X is root 2 sine theta. And dx is root 2 cos theta d theta. Now at this point you'll want to tidy this up, so I'm going to just divide, these are factors, I'm going to divide those out, and I'm left with cos theta times cos theta, so I've got cos squared theta over sine of theta d theta. Now, unfortunately at this point, the way it's written is not a direct pattern that we can set up. It's not a chain rule. It's not a direct trig derivative. So I think what would probably be best here is to put a trig identity into this one, change it to 1 subtract sine squared of theta, leave the bottom as sine of theta. Now, what that allows us to do is split this into two separate integrals. The integral of 1 over sine theta d theta minus the integral of sine squared over sine, which is just sine of theta d theta. Now this is an easy one because that's one of our differentiation rules. This one is going to be relatively easy, at least it's one that I showed you how to do in a second. 1 over sine is cosecant. And I showed you a little trick to integrate cosecant and secant. And the way it worked was you multiplied, if it's secant, it would be secant plus tan. If it's cosecant, you multiply by cosecant theta plus cotan theta. Now, somebody had the right answer here below this, but you didn't show this step. I would suggest you show this step just so you indicate to the person who's marking your work in the future that you know what's going on. And you didn't just take the answer from a photo math or something like that. Sine of theta, the integral of sine of theta is negative cos. And there's already a negative here, so this is going to go to plus cos of theta. There's going to be a plus c at the end of this. Multiply this one out, so you're going to get cosecant squared theta plus cotangent squared theta over. I'm just going to switch the order of these, or they're added, so the order they're added doesn't matter. And the reason I'm doing that is because the derivative of cotan theta is negative cosecant squared theta. The derivative of, oh, what did I do wrong here? This one should have been this multiplied by this should have been cosecant theta, cotangent theta. Forget that our d theta stuck it here at the end. Okay, let me try that again. Cosecant squared theta is almost the derivative of cotan theta, just missing the negative. The derivative of cosecant theta is almost this, just missing the negative. So technically, if I just multiplied the numerator by -1, right, all the way through, that would make both of these -1, and then just put another -1 out front to offset that, I would now have du over u, which would be a natural log. So this would be negative natural log of cotangent theta plus the cosecant of theta, and then I've got plus cosine of theta plus c. Then you can just go back to your triangle that you've drawn earlier and you resubstitute whatever these values are. So let's look for cotan of theta. When I look in my triangle, cotan of theta, here's theta, cotan theta will be this over this. So square root 2 minus x squared over x. Going in here instead of square root 2 minus x squared over x plus the cosecant of theta. Back to your triangle, look at your triangle. Cosecant would be this over this. It's a reciprocal of sine. So radical 2 over x. Just thinking here, I think I forgot it. Radical 2 up here somewhere. Yeah, I did. This radical 2 disappeared on me. I should have. See this one here? That was still there. That should have been down here all the way through. So it'd be a radical 2 there. It'd be a radical 2 there. So it'd be a radical 2 here. And it'd be a radical 2 in front of this. That would make this square root 2, square root 2. It'd be a radical 2 in front of this here. And we're good to go. Plus radical 2, the cosine of theta. The cosine of theta is right here, radical 2 minus x squared over radical 2. Minus x squared over square root of 2. Once we're done, put your plus c. There would be that interval using trig substitution. I think that's probably the easiest way to do it, not the only way. I believe there was one other solution that I corrected that was correct, but it didn't use a trig substitution. So I think it was a little bit more difficult, but it did work. On to B. Almost a dead giveaway is when you see one angle x and you see the other one is 2x, is to use a double angle identity. And there's a double angle identity for sine of 2x that says the sine of 2x is the trig identity you learned in grade 11, 12a. 2 sine of x, cos of x, dx. Multiply that out. And you're going to get cosine to the 4th x, sine of x. The 2, I just throw that out front. So now, at this point, you've got a chain rule. You've got u to a power, just about du. The only thing missing is a -1, so we quickly, easily fix that. There's a negative. There's a negative. Now it's not subtracted. If you realize that's multiplied by. So now I've got u to the 4th with du sitting right next to it. That's chain rule. So to undo chain rules, you add 1 to the exponent and divide by the new exponent. So this will be -2/5 cos to the 5th x, not -2/5. Sorry. Yeah, it is -2/5, but no 5 down here. I already divided by 5. So I added 1 to the exponent to go to 5, then I divide it by the 5. And then normally it's plus c, but this one is definite with the bounds. So 0, pi over 2. Should be relatively easy substitutions. I'll just draw, this is the graph of cos x. So at 0, you can see that, the reason I'm doing that is so when I go to do my substitution, it's going to be -2/5 cosine of pi over 2 to the 5th minus -2/5 cosine of 0 raised to the 5th power, and that's going to give me my answer. So the cosine of pi over 2, well, here's pi over 2 right here. The cosine of pi over 2 is 0. So this is going to be negative 2/5. 0 to the 5th power is just going to be 0, minus a negative 2/5. The cosine of 0, here's 0. The cosine of 0 is 1. That's to the 5th power. So this is all going to be 0. 0 minus a minus 2/5. Final answer should have been 2/5. All right, now we go to the next one. Okay, this one, Princeton. I don't know if you're familiar with Princeton. Princeton is one of the more prestigious Ivy League schools in the world, based out of the United States. So you know you're dealing with challenging questions. So I'm going to take this and set it into partial fractions. I'm going to do that work over here. So it's going to be a over x plus 1 plus bx plus c over, now the reason I have to do this is because, and all of you did this correct, is because this is a non-factorable quadratic. Squared 6x plus 10. So you get a common denominator, which would be x plus 1, x squared plus 6x plus 10. First fraction, I got to multiply by this to get my denominator to be correct. My second fraction, I'd have to multiply by x plus 1. So at this point, I'm going to abandon the denominators. They don't really matter because it's already the same as this one. This numerator needs to become the same as this numerator. So I'm going to expand it out. Ax squared plus 6ax plus 10a plus bx squared plus bx plus cx plus c. So that's the numerator of this. Well, that has to be equal to, switch colors here, the original numerator, x squared plus 3x minus 3. So let's make some equations. Let's do the x squareds. So a plus b, the coefficients of the two x squareds when combined have to give you this coefficient. So I know that a plus b has got to equal 1. Let's do the x's. So 6a plus b plus c has to equal 3. 6a plus b plus c has to give me a 3. Those are the coefficients in front of the x's. And now your numeric terms, the ones that don't have any variable attached to them, would be your 10a plus c. Those two, when combined, would have to give you a minus 3. Probably your best bet is to rearrange this one into something to put in there for a or b. Let's say I go with b. So b here is 1 minus a. I'm going to take that and put it in here for b, so that makes this equation have only a's and c's in it, and then this one will only have a's and c's in it, and I can combine these two to solve for a and c. So it's going to be 6a plus, instead of b, put 1 minus a in there, plus c equals 3. So now I've got 5a plus 1. No, sorry, let's go plus c. Let's take the numbers to the other side. So that 1's going to go over there. That's going to give me 2. Let's take this one. 10a plus c equals negative 3. Well, the c's are all lined up perfect. Let's eliminate. Subtract. So let's go this way. 10a take away 5a, that's 5a. C take away c, that's 0. Negative 3 take away 2, that's negative 5. That tells me a has to be negative 1. Well, once you get one number, then it's usually an easy task to get the rest of them. So let's go here to get b. B is 1 minus a. So b's got to be 2. And then c, let's go here. 5a plus c's got to equal 2. So 5 times a plus c has to equal 2. So that means c has got to equal 7. All right, so I've got my values for a, b, and c. I rewrite my integral. So this integral this integral is going to be written in this form instead. And the process you just did, or watched me do, is called partial fractions. Okay, so A, here, so this would be the integral of -1 over x plus 1 dx. That's easy. That's ln of u, du over u. Now the next one was the challenge. So it's the integral of bx plus c over x squared plus 6x plus 10. So this one had an extra challenge. What they wanted you to notice as you're doing this is saying, oh my goodness, if this was just a 6, this would be perfect. Because the derivative of the denominator, x squared plus 6x plus 10, is 2x plus 6. I've got plus 7. So what they wanted you to do, and we had not done this, so credit to somebody or whoever was able to research and figure out how to do this. And you're welcome to do that. I want you to do that. I want you to ask me questions. I want you to ask your classmates questions. I just don't want you to get a picture of their work and copy it so you have no clue what's going on. What they do here is they split this. So it's going to be the integral of 2x plus 6 over x squared plus 6x plus 10 dx, because that's du over u. And then that leaves an extra 1. So then you need the 1 over x squared plus 6x plus 10 dx. And you got this one already, which we already said is easy. So it's just negative dx over x plus 1. So this is du over u. This is du over u. This one is not du over u, but it is a pattern that requires you to complete the square. And again, credit to somebody who was able to find an example of this, because I did not go through it. I actually did have it in my notes, but I kind of jumped over it, not unless you'd see it here. But again, that's part of life. You got to, sometimes when you're, especially if you're sitting there with the internet in front of you, you can figure stuff out if you want. All right. So what they want you to do is take this x squared, I'm just going to do it here, x squared plus 6x, and you're going to complete the square. So this is usually used when it's just a number, any number, over a quadratic. And now you take half of this, which would be 3, and you square it. So you're going to add 9, add that at 9, which means you're going to take away 9. This is now x plus 3 squared plus 1. Now that is, let's just look at that integral. So it's the integral of 1 over x plus 3 squared plus 1 dx. So one of your rules for integration or differentiation, the derivative of arctan x is 1 over x squared plus 1. Well, instead of x, this is just x plus 3. And then you need your dx up here, sorry. Because if you have x plus 3 as your u here, your du would just be 1, which I've got. So this is arctan of x plus 3. Okay, let's put that all together and integrate each one of these. So here's my final answer. Negative natural log of x plus 1 plus natural log of x squared plus 6x plus 10. And then last but not least, inverse tangent of x plus 3 plus c. All right, one more to go. All right, so this is the one that I believe, as I showed you in my introduction, many of you shared a solution, just copied it, really not quite sure what went on here. In this one, it's pretty typical of natural logs combined within natural logs. Now again, you don't have the exposure to calculating integrals that's probably necessary to look at that right away and say, oh yeah, I remember doing one like this before. Well, guess how the only way that's going to happen? The only way that's going to happen is by you doing as many sample integrals as you possibly can. They don't have to be just ones I give you. As I said, the internet's full of them. You can find examples. You can put this into Google. I'm sure it would show you how to integrate it. But taking that and then copying it without understanding what's going on is not an effective way to make sure you understand what's going on, so that when it's exam time or midterm time, because yeah, we may end up doing some online learning in the future, you're still going to be tested individually so they can see that you know what's going on. They're not going to let you sit at home and do exams and midterms. You're going to have to go in and write those. So you're going to have to make sure you understand the work. Okay. I'd be inclined to start with a U-substitution, but I'll show you what I did, just to exactly. When I would do my answer key, I went U equals ln of x. The reason I did that is because du would be 1 over x dx, and there's 1 over x dx in this question. There's my u. So this question then became the ln, so ln of x is u, right? It's right here, ln of x is u, so ln of u, dx over x is du. This question, if it had been presented as ln x dx in the beginning, hopefully would be dead giveaway integration by parts. But what I don't like here, when I got to this, I said, oh, I've already used up u. I like the formula. Just seems to roll off my head a little bit quicker if I use u and v as uv. So the integral, let me back up. So the integral of u dv is uv minus the integral of v du. But there's already u's in here. So I said, oh, I don't want to use the same letter. So I just went back up to the top here. I think I'm going to switch this. I use w. So just switch instead of u substitution. That's just a random letter. Just don't pick the same letter that's here. So w substitution. In the one that many of you turned in, you use t. That's common. I'm just going to go w. It was easy to turn u's into w's. And then this was ln of w dw. So now I'm not repeating the letter u in my integral and my formula, because then that gets confusing. Okay, so now we should be good to go. I'm going to let you, watch how I do it. I don't do it the way that you folks passed in, many of you. I let u equal, in this case, ln of w. And then beside it, I always let dv equal, in this case, it would be dw, and then I work down. So du would be 1 over w dw, and v would be the integral of this, which would just be w. So now I go here and do my substitution. So it's uv, so uv, w ln of w minus the integral of v du, v du. Those are gone. Now I'm down to w ln of w minus the integral of just dw is all that's left here. Well, that's just w plus c. Now I'll go back and say, what the heck's w? W is way up in the beginning. Everywhere you see a w, you're going to replace it with ln of x. This would be my final answer. W is ln of x. Ln of x minus ln of x plus c. Many of you had the factored version of this, which again, I don't think you really understood what was going on. You factored out ln of x. You didn't. The answer you found had done this. And it ended up looking something like that. I wouldn't do that. It's not wrong. Again, that's the answer that many of you presented. It was the common factor ln of x being factored out to make it look like this. This is where I would have stopped, right here. Okay, so as we move forward, again, I'm being as fair as I can with all of you. I'm not asking you to turn in abundance of work, but that doesn't mean there's not work you should be doing. Think about it on a regular basis. If you were in school, we'd be spending 5 hours a day in a classroom working on this stuff. That's being now put on you to do on your own. So it's important that you're putting the time into this at home, and it's important that when you're stuck, you're asking questions so that we can get things straightened out. It has to be questions of, I've tried this, I'm stuck here, can you have a look at this? To just randomly say, I don't understand any of this, that's no good to me. You have to take the time. Okay, you're smart young minds. You have to take the time to research, watch the videos that I do, stop the video. When there's a question, try it out, watch my solution. That's the way you'll get better at them. Yes, there will be a challenge in the beginning. They will get easier if you put some time into this over the next few weeks. All right, so hopefully I'll hear from some of you as you get into problem set A, and we can do some discussions and work through any problems that we run into with those. And just because you get stuck on maybe part B or C, it doesn't mean the next one's going to be more difficult. Jump to the next one. Just try and do the best you can with all these practices. And I'm going to just keep throwing up sets of integrals that they're just random now. We probably will, toward the end of next week, look to collect another 4 from you, demonstrating that you understand, hopefully, even better now than you did prior to last assignment. Okay, so good luck with the integration. And again, please reach out when you're struggling.